Okay, well, let's begin. So, plan for today is we're going to continue walking through chapter 4, which is going to be going in some detail through the action potential. We're going to be talking about sort of each requirement of the thing and trying to build upon what we did last time in terms of looking at and using the golden equation and the concepts of the golden equation to understand what's happening at a cell membrane that's going through an action potential. Bless you. Monday, there is homework for chapter 4 that's due, and we should have time to be talking about it at least in groups and probably a little bit as a class as well. And then probably on Friday, I want to plan to do a quiz on chapters 3 and 4. It won't be an especially long quiz. It'll just be sort of combining both topics. You should plan to bring a calculator. And as I've said, if you want to use the one that's on your phone, I'm okay with that as long as you promise to only use it for calculating things. Just make sure you know how to use your log button. I think that's the key thing. Any questions before we start? Okay, so we kind of introduced the idea of action potentials last time. And I know you guys, many of you have had stuff about them in other classes, but we're going to be going through it in more detail today. So the goal is that we're going to start with kind of a theoretical action potential, talk about some of the major players, and then flesh it out a little bit with some additional details to get to a model that matches very closely what seems to happen in reality. And then once we understand what's happening at one spot on a membrane, which is where an action potential might occur, then we'll talk about how those are propagated along the length of an axon. And that's pretty much the end of the chapter. So how do we make action potentials? So our goal is to come up with basically a model for how action potentials can work. And the model, based on what we've already seen about action potentials, needs to have a few different components. Whatever we do, we need to have some way for the neuron to respond to an initial stimulus, and usually this is going to occur somewhere out on a dendrite. I'm sorry. But action potentials are confined to axons. No idea he was there. Like, scared the crap out of me. That's all right. Yeah, so this is largely something we're going to actually push to chapter 5, so I'm not going to spend a lot of time on how we initiate an action potential for now, but we are going to be focusing on like one spot on an axon and talking about what's happening there and then how we propagate. Any action potential model has to feature some sort of massive depolarization. Right? So we need to have a massive upswing in membrane potential, and each one basically should have the same amplitude as we sort of execute an action potential on a membrane. So every time it does that, each action potential should more or less be about the same as all the other action potentials. After it has your massive depolarization, we need to have a subsequent repolarization. So we need to get back down to resting membrane potential. And we need to have some kind of mechanism that will prevent any kind of stacking from occurring, because we need to have some kind of finite limit to how quickly you can fire an action potential. We talked about frequency of action potentials is how we encode information, but there's got to be some way that there's some kind of stacking preventer, and those turn out to be the absolute and relative refractory periods, and we're going to talk about exactly how those things work. So what's the mechanism behind that? And then, of course, there's got to be some way to propagate these action potentials along an axon once they begin. So we're going to progressively try to build a model that does all these different things. And it's not horribly complicated. And in fact, if we just think about what we started in chapter 3 last time, in the last chapter, we talked about how if you just start changing permeabilities of ions, you can get massive swings in membrane potential. So if we sort of start with this first goal that we need to have a depolarization and then a subsequent repolarization, we could probably think about, okay, if we're starting from a very negative resting membrane potential, what could we then do to cause a change in the membrane potential and cause that big depolarization? So here's a model sort of building upon chapter 3. And the idea here is that membrane potentials are going to be caused by ions moving across the membrane, and different ions will have different effects on the membrane. So in this picture, it's showing a cell where the equilibrium potential, and that would be built entirely really on the concentrations of the ions, the equilibrium potential of potassium, it says, is minus 80 millivolts, and the equilibrium potential of sodium is plus 62 millivolts. Those pretty much should match the numbers we were calculating on the homeworks and such. And those are pretty typical values for those two ions. So that basically means that potassium's at high concentration inside and would stream out of cells to make the membrane potential become negative. And sodium would be at high concentration outside of these cells, so that when you open channels for it, it would stream into the membrane and make the inside of the membrane more positive. Okay, we're starting from a circumstance here where there's no permeability. So in this case, if there's no permeability, so no channels are open, which is what this picture is showing, in that case, if you look at Ohm's law, if there's no permeability, that means this term, conductance, that G term right there, should be 0. And if there's 0 conductance, that means that there's going to be 0 current moving across the membrane. So this is kind of just like a default. I don't even know if it's a default. This is a no permeability at all, so we don't have anything interesting going on. So if there's 0 conductance, there'd be 0 current, and consequently, really, there's going to be 0 membrane potential. So that's what this term is the difference between the current membrane potential and the equilibrium potential of an ion. In this case, it's highlighting potassium. And I just said all that. So at this point, because there's no current, we don't have anything interesting going on, but we could start to have some kind of a potassium current if we just were to open potassium channels. And so as long as we've got some potassium channels that are open within our sort of a fictitious cell that we're building here, that's going to cause the membrane potential to move towards the equilibrium potential of potassium. And really, if potassium is the only thing that's present, you can plug all that into Goldman, and Goldman's equation will tell you that the membrane potential will eventually become the equilibrium potential of potassium. So at this point, if you start from scratch, before with the membrane potential starting at 0, and you suddenly open some channels, now you'll have potassium ions streaming out of the cell. That'll drive the membrane potential. Initially, the membrane potential, which is Vm, voltage of the membrane, is very different from the equilibrium potential of potassium. So initially, there's a strong ionic driving force, we would say. The difference between Vm and Ek is very large, and therefore we'd have a nice strong current of potassium ions moving out of the cell. And that would occur until such time that the membrane potential shifts and becomes the same as the equilibrium potential of potassium, which is what's happened here. So in this case, we've had so many potassium ions leave that now there's a lot of positive charges just outside the membrane, and the inside of the membrane is quite negative. And so now potassium ions are leaving the cell by its concentration gradient at the same rate that they're coming back in by the electrical gradient. So at this point, our membrane potential has moved to be minus 80. It says that somewhere. Here's voltage of the membrane is now minus 80. And therefore, if you look at Ohm's law, there's no difference between the membrane potential and the equilibrium potential of potassium. Okay, and so at that point now, we're not going to have a current. So if Vm minus Ek, if these two terms, Vm and Ek, become the same, then the difference between them is 0 once we've hit our equilibrium potential. And so at that point, now there's going to be, even though there's still permeability to potassium, there's going to be no current to potassium. Does that all make sense? I mean, we haven't done anything new really at this point. We're just sort of setting up a situation where now we've got a cell with a lot of potassium permeability. So there's good conductance to potassium, which is the G value. And because of that, the membrane has changed such that now the membrane potential is matching the equilibrium potential of potassium. And this is basically our state at our resting membrane potential. We can even draw a picture, and I think I will, of the membrane potential at this point. So if this is our membrane potential, voltage of the membrane, Vm, and this is just going to be basically time, we at this point are at about minus 80 millivolts. We're at the equilibrium of potassium, and the membrane would just be kind of holding steady at this point by the time we get to C. So now what we want to do is mess this up. So we've got a resting membrane potential, but we want to change the membrane potential somehow. So what would happen in a typical neuron is you'd have some sort of an external stimulus. So I've got sort of a one slide sort of summary of this, and again we'll come back to this idea when we get to chapter 5, which is where we're going after this. So this is my little bad picture of a neuron. Looks a little bit like a squid, sort of. But in this case, what you've got is we have dendrites out here branching off of the cell body, and these dendrites would have receptors. These receptors would be sensitive to some kind of a stimulus. It could be a stimulus coming from another neuron, so it could be neurotransmitters, for example, coming from a different neuron. This could be a touch receptor, and therefore these could be pressure-sensitive channels. It kind of doesn't matter for our purposes, but there's some kind of a stimulus that's going to occur out here at the end of one of these dendrites that's going to start a little bit of a disturbance within the cell. This little disturbance is what's called a generator potential. So we have this localized disturbance right out here on the tip of the dendrite. And that generator potential is then going to be relayed down to the cell body. Oftentimes what will happen when you have a generator potential out on a dendrite, so in this case on the slide rather, I said maybe a pain receptor gets stretched. I mean, it could be any kind of a stimulus. What will typically happen is it's oftentimes some kind of a sodium channel opening. If sodium channels open, so if that little red thing that I'm showing is a sodium channel that's opening in response to a stimulus that this membrane out here on the tip of the dendrite is experiencing, that will then cause, where's my pictures? Here's sodium ions. They might start entering into the interior of this cell. Okay, so the sodium channel's opening, that's my little black box, and now sodium ions have rushed into the interior of the dendrite. Okay? Once they've done so, these ions that came in, those are ions. They are free to move around within a solution. They're bouncing around randomly. So some of them will probably go the wrong way, but some of them will happen to bounce their way down down the dendrite into the cell body of this neuron. So that's what this is going to show. No, it didn't quite. I was trying to get it to go like right along the thing, but that's the idea. So we've got positive charges from these sodium ions that came in over here that form a generator potential, which would be a pretty strong disturbance, but it's localized out here on a dendrite. But some of those positive ions that came in would literally diffuse their way down into the cell body, and then ultimately would start to enter into the region right at the beginning of the axon. This is what's referred to as the axon hillock. And it's basically just, it's an offshoot of the cell body. This is where you start to find the very first special kind of channel that's present on axons, and these channels are called voltage-sensitive or voltage-gated sodium channels. Basically, these are little channels that have the ability, they have a particular property, and on the homework it actually goes into and gives you a chance to see what that property is, like how these things work. They're just little machines. There's nothing magical about them. They can detect changes in voltage, changes in charge environment around them. And if you get enough of these ions coming in from the dendrites, getting down into the axon hillock, then they will start to open down here in the axon. And so what's happening now, if I have these little sodium ions coming in, those are going to cause the axon then to undergo a big depolarization. We'll walk through that quantitatively in a second. And basically, this is going to trigger an action potential to occur right here, and that is then going to be propagated all the way down the axon. Okay, so let's zoom in and try to understand, once we get some kind of an external disturbance, and again, this is mostly chapter 5, but here we've got ions coming in at some receptor. That's going to make those ions make their way down to the axon and cause some initial disturbance. Once that happens, what we want to focus on is what's happening here in the axon, which is how these voltage-sensitive channels might then cause a change in the memory potential. Okay, so here is this is sort of an idealized model of how we could create something that looks sort of like an action potential. So we're starting at a resting memory potential. That's where we are up in this picture at the top in A. So that's what we had at the bottom 2 slides ago, where we have potassium channels are open, and that is the only ion that is permeable at this point. And therefore, the memory potential exactly equals the equilibrium potential of potassium. The ions have shifted to such a degree, or moved to such a degree, that we have a balance between the concentration gradient of potassium and the electrical gradient that is established across this membrane. So ions are going in and out. Potassium ions are going in and out at the same rate. So we are at the equilibrium potential of potassium. Now what we're going to do is all of a sudden we could start to open some of these voltage-sensitive channels, and they're opening in response to these other ions that came out from the dendrites and have cruised down into the axon. Okay? So here, these are little sodium channels, these blue ones. These guys start to open all of a sudden. If they open, that is going to increase the permeability of sodium, or permeability of the membrane to sodium. And so that means now sodium ions can start rushing across the membrane. They are at higher concentration outside than they are inside, so they start moving from the outside to the inside of the membrane, and they will make the inside of this membrane now become more positive. So that's what you're seeing here. We started at resting, and now we're starting to depolarize. And we could depolarize depending, if we opened a bunch of sodium ion channels all at once and had tons and tons of sodium ions rushing into the cell, this could cause a massive depolarization, like we see in a real life action potential. Okay. That means that these voltage-gated sodium channels are responsible for the depolarization phase of this idealized action potential here. That gets us up, and we've depolarized. So now all we need to do is get back down to resting membrane potential. So, one simple thing we could do without introducing any additional kinds of channels is we could just, I guess we've already done the rising phase, we could just close all these sodium channels there, right? I mean, we opened a bunch of them. That's what's causing the membrane to become more positive. If we just close them all now, that would then get us to a situation where potassium is the only permeable ion. So ions would be able to stream across these potassium channels, and they would remove positive charges from the inside of the membrane and take them to the outside of the membrane, and they would keep doing so until such time that the membrane shifted all the way back down from being very positive all the way back down to match the equilibrium potential of potassium, which is back down to -80. So all we had to do to get the membrane to, all we had to do to get the membrane to change is change the permeability of sodium, really. We started with lots of potassium permeability and no sodium permeability, and we were at this resting membrane potential state. We depolarized by opening a bunch of voltage-gated sodium channels, and then we closed them, and that would cause the potassium ions then to dominate again, and they would cause the membrane potential to drop back down. So we've gone up and we've gone back down. Yeah?
So, just to kind of clarify.
Uh-huh. Right.
And as it depolarizes, the potassium channels are closed. But then
No. Yeah, actually, these potassium channels just stay open all the time.
so they're open the entire time. So, okay, but sodium channels are open.
Yes. Yeah, so the membrane won't shift all the way to sodium's equilibrium potential here. We're not going to quite hit that point because at this point, there's still potassium ions that can move across their channels. We haven't disabled potassium at all. All we've done is kind of done what we did in the Golden equation, where we now, instead of just having potassium be permeable, now potassium and sodium are permeable. And usually it's to such a degree that the permeability of sodium, it's really small writing, but you can see it over here. The permeability of sodium, or conductance of sodium, is much greater than the conductance of potassium at this point. So there's just massive numbers of sodium channels opening during this time, and it just overwhelms the potassium channels for the most part. But they're still there. They're still having an effect. They haven't closed. Okay. So I think this is really cool. We have simply, by changing sodium's permeability, opening sodium channels and then closing them again, we can cause the membrane potential to depolarize and then repolarize in pretty massive fashion. And, this isn't quite to a real-life action potential, but it more or less does what we need it to do. Right? It's pretty much all due to these sodium channels, or at least we can get the effect that looks a lot like an action potential just from these sodium channels alone. Okay? Any other questions so far? So, this is sort of reconstructing work that was done, mid-1900s, where they were starting to look for these sodium channels. And they're like, if this is one mechanism, at least, by which we could cause the change in membrane potential, the cause in membrane, I need to say that again. This is one mechanism by which we could cause the change in membrane potential that we see during an action potential. So if that's true, we should be able to find sodium channels, these voltage-sensitive sodium channels. So how do we do that? Here's a way. This is called a patch clamp method. And this is a mechanism by which you can isolate individual ion channels. So if you're on a hunt, you're looking around on axons, and you're trying to find individual sodium channels, this is one way that one can actually go after them and try to isolate them and study them individually. So again, it's called a patch clamp. It's a cool little technique. It's one of these things where I think it'd be really cool. It's also, I'm sure, extremely finicky. And you'll see why, I think, as I describe this. The goal here is that we're going to try to get one little sodium channel to be present and isolated from all the rest of the sodium channels that would be on a membrane within a glass electrode that we're creating. So what you do is you create a glass electrode, and glass electrodes basically are little ion, like saltwater filled tubes made of glass. Literally what you usually do is you get something that looks a lot like a hematocrit tube, if you've ever done a hematocrit thing like an A&P lab, and you heat it, at least this is the old-fashioned way to do it. You heat the glass just enough that you can pull it apart, and so you pull it apart in a nice smooth fashion, and it basically causes the entire tube to narrow down to a really narrow diameter tube, but it still has a little bit of a tube inside it, ideally, if you do it right. So you stretch out the glass, you break it, and then at that point you've got what amounts to just an incredibly small microscopic scale syringe, or microscopic scale needle, that you can press up against the side of a cell. We're not actually going to stab a cell in this case. We're just going to press it up to the side of a cell. So you stick that really, really fine glass tube, and the tube you actually fill with a saltwater solution, a saline. You press it up against the side of a cell, and you have to use a micromanipulator at this point. You can't just do this by hand. So you have a little device with little gears, and you press it up against the side of a cell. And then you add just a small amount of suction, just for a moment. And if you do it right, that will suck just a little bit of membrane into the interior of your pipette. So this is ideally what you've done. You haven't separated the membrane at all. You've just sort of sucked a little bit of membrane into this, into your tube. It's like a pipette. This is your glass electrode. And now you have this one, I mean, if you get really lucky, and you would have to do this over and over and over again, I'm sure, but if you get really lucky, you'll get an individual ion channel, in this case a sodium channel, present within this pipette tip. So you've got basically now a way that you can measure the charge difference just across the membrane and even ion flow across this individual little channel. Without getting too much into the details, because you have to do these voltage clamp devices, which I don't want to get into. But basically you're able to monitor using your electrode the current passing through any channels that happen to be within your little pipette tip here. And so what they're doing in this case, this is actually recordings of the current passing through your electrode. And again, any current that passes through your electrode also has to pass through the channel that your electrode contains. So you're kind of going along, you got a lot of current, but it's all sort of an outward current. And then all of a sudden, you get these little blips like that. Here's another one, and there's a nice, really big long one. And there's another one, there's a huge long one, right? So what these downward swings are indicating is that these are inward currents of sodium ions that are going through the channel that you happen to capture with your little patch clamp recording. Whoops, I didn't mean to push that button. So this is a way you can actually observe these little individual channels. And then what you can do is you can start to manipulate the environment of the overall neuron while you're recording from that one channel. And so like one thing you might be interested in once you isolate an individual sodium ion is, do these channels actually have the ability to be responsive to changes in the membrane potential around them? So that's actually what we're depicting on this next slide here. So these are measurements from real sodium channels. So the way this slide is set up, you can sort of imagine you've got an individual neuron here. And on that individual neuron, you have 3 discrete patch clamps, each of which is anchored over an individual sodium channel. So this is one patch clamp recording. This is a second one. This is a third one. And all of these are on the same cell, recording from the same cell at the same time, from probably pretty close to the same place. But these are 3 independent channels that you're recording from individually here. Then you've got another electrode, and this other electrode is impaled into the cell at a different site. And that electrode then can be used to change the voltage of the memory potential. You basically just inject current or remove current from a cell, and you're actually able to change the memory potential without having to worry about dosing a neuron with neurotransmitter or anything else like this. It's just sort of a nice direct way to cause a change in the memory potential just by driving current into the cell separately. So this is kind of an artificial stimulus, but this is oftentimes how people do it when they're doing electrophysiology, is you directly stimulate that individual cell. But you can imagine in real life, this would be like dosing this neuron. Every time we do this little upswing here, this would be like dosing this neuron with a neurotransmitter, or stimulating a pain receptor. It's the external stimulus that we're creating here using this voltage device up here. So what they do in this study is they're starting down at the resting membrane potential of a neuron. We're starting at minus 65 millivolts. And then this other electrode we use to inject some positive charges, basically, into the interior of the cell that causes the membrane potential to change such that we start at minus 65 and we move all the way up to minus 40 millivolts. So we're basically depolarizing it. We're not causing an action potential, at least not directly. We're not depolarizing it super far, but we are depolarizing it a substantial amount from minus 65 up to about minus 40. This would be about equivalent to what threshold might be in a neuron, which would get this process started. So that's the stimulus, and then what we want to do is record what happens to the individual sodium channels during that stimulus. And you can see what happens is, in this case, we depolarize where the dotted line is here. That's sort of our initial external stimulus. And all of a sudden, you start to see these individual sodium channels open and then very quickly close. So that one opens pretty much right away, the first one. The second one over here, it takes a little bit longer for it to respond, but eventually it opens and then it closes. And it was open for about the same period of time, at least, once it started. This one took a little while to start and then was open a little bit longer, but then it closed. And the other thing I'll point out is that they all open close to the same moment. I mean, there's a little bit of a scatter, but they're all opening more or less right away once you change the charge environment around them. And they stay open for a pretty short period of time, and it varies from channel to channel, but then they close. And they never open again, even though we're continuing to apply that current, so we're continuing to provide the exact same stimulus. These things will not stay open. And in fact, the only way we could ever get them to open again is if we relax this current, let it reset down to minus 65, and then depolarize it again. And at that point, we could get them to open again. So what this is showing is that these channels have the ability to open in response to the depolarization. And once they do open, they will stay open for a very brief period of time. This is equivalent of about 1 millisecond. That might be slightly longer than 1 millisecond, but it's about 1 millisecond that they're actually open. And once they close, they become inactive. They cannot open again until the resting membrane potential, or until the membrane potential returns to this resting membrane potential. So if they did another experiment right after this one, that would kind of go off onto the wall over there, and depolarize it again after getting down to minus 65, we get these channels to open a second time. But it wouldn't open again until we get to that moment. So that means that these channels open. They stay open for a brief period, and then they become inactivated and will not open again until the membrane returns to the resting membrane potential. Does that make sense? More or less. Here's what we think is actually happening. There are charged domains of the protein that are present within this protein complex of the sodium channel. And this is what the homework question is about, so I won't spend too much time on that. But as you start to depolarize the cell here, that changes the charge environment around the membrane, which causes that subdomain of the protein that is charged to shift. It's basically responding to the change in charge around it. And that would cause the channel to open. And then the cool thing is these things stay open for a little bit of period of time, but you see they've also got this little globular subunit down here. This is basically going to function as a cork. It's a cork on a string. And it would, if these things are small molecular level structures, so this thing is always kind of bouncing around randomly. And once you open this channel, this thing will bounce around for a while, but eventually it's going to bounce into this opening, and once it does so, it sticks, and it corks closed your voltage-gated sodium channel. And it will basically stay in this state until such time that the charge environment around the channel returns back to its sort of resting state. And at that point, the charge domains kind of get pulled downward. That then forces the cork out, and the channel is able to reset. So now we're back to that point, and we could open it again once there's a new stimulus. So the idea is, it's the charge environment changing that causes the channel to open, but then it inactivates moments later because this cork inevitably is going to bounce into the hole and seal it up. So it's called a globular subdomain. And that globular subdomain basically just plugs the pore after the opening. And the plug will only be released when the memory returns to the resting memory potential, which allows the channel to reset. So what this means is the first time you stimulate a neuron, that sort of brief moment that you initially stimulate a neuron, you'll get lots and lots of these sodium channels opening. We only are recording from 3, but there would literally be thousands and thousands and thousands of them on just a tiny stretch of axon membrane. And they would all more or less open at once, and then they become inactivated and close again. And they could not open again until you get your memory potential back down to resting. And so that's what causes what we call this absolute refractory period, where once you stimulate a neuron, it'll basically fire an action potential one time, but then it's got to get a chance to reset before it can fire another one. So it sort of causes an upper limit to how often you can fire. A little more detail on sodium channels. These things are interesting because they are very specific, just like we saw with potassium channels. So the potassium channels only really let potassium go through. Sodium channels are built in kind of a similar fashion. So like potassium channels, they're composed of subdomains, and the subdomains are lined on the inside. So this would be a sodium channel. And each sodium channel would have these different subdomains to it. And then there's this little pore loop attached to each part of the sodium channel, and these pore loops line the inside of the channel. So this is just the same sort of setup we saw with potassium channels. But it's sized just slightly differently, so that in this case, the channel is just big enough to allow a sodium ion. So that's what this is. So this is size of sodium channel selectivity filter. Basically, this is just saying this is the size of the channel. So if this is the size of the channel, that is just big enough to allow a sodium ion as well as a water molecule that's associated with it to enter into that filter and pass through the channel. Whereas if a potassium ion, which is the other really common positively charged ion, tried to also go through that same channel, in this case the channel is just sized a little bit wrong so that the potassium ion and that water molecule can't quite fit, and as a result it does not readily pass through this channel. So these are very specific for sodium, and they do not allow potassium ions to go through because basically just potassium ions are too big and they won't fit. So what this is telling us is that we have these little voltage-gated sodium channels. They are present all over the axons. They're very specific to sodium, and they will open very briefly in mass in response to a change in the voltage environment around the axon. It's kind of our smoking gun, really. I mean, this is exactly what we need for that initial model to work. Any questions so far? Okay, so what I gave you before was frankly a pretty simplified model. There's a couple problems with it. One of the problems is that while we did get a nice upswing and we did get a nice repolarization, the repolarization, if you actually run calculations and quantify everything, just by closing sodium channels alone to cause a repolarization, the membrane doesn't repolarize fast enough. It doesn't respond as quickly as we would expect it, and we actually observe actual membrane potentials to respond in an action potential. So, you can sort of imagine if you overlaid our model to this trace, so this is like a real action potential, we would get a rising phase that would look about right, but then our repolarization phase would kind of go like this. So it would be much more slow, and we wouldn't get back down to resting membrane potential as quickly as actual real neurons do. Furthermore, actual real neurons have this weird little undershoot, and our model doesn't explain that at all, right? I mean, we just see going back down to resting, and we stay at resting. At least that's what my picture's supposed to show. So we need some way to explain how we get a very rapid repolarization phase, or falling phase, and we need to explain this undershoot somehow. So The answer to this is that in addition to having these little voltage-gated sodium channels present on the membranes of these cells, we have one other kind of channel present, and those channels are called slow voltage-gated potassium channels. They're called slow because they don't open as quickly as the fast sodium channels did. So what we've been talking about are more like these fast sodium channels. Slow potassium channels open more slowly. So the idea is we've got three kinds of channels we've been talking about. We have one, the first ones we were talking about are called potassium leak channels. These are basically always open. So leak channels do not have gates. They are never going to close. They are always open. And so these things are always, always, always allowing potassium ions to flow down their concentration gradient. And this is basically, these potassium leak channels are what's responsible for the resting memory potential. They would cause the membrane to become more negative on the inside as positive charges leave. Then we talked about voltage-gated sodium channels. Voltage-gated sodium channels do have a gate. I'm going to draw the gate as like a little door. Voltage-gated sodium channels would allow sodium ions to enter. Now we've got a third kind of a channel, and these are voltage-gated potassium channels. And voltage-gated potassium channels would allow potassium ions to leave, because potassium ions are potassium ions, but this is a different population of channels. These guys do have a gate to them. And so they will only open when there's been some sort of a change in the charge environment around these channels. So these are voltage-gated potassium channels. And again, we call them slow voltage-gated potassium channels because they take a little bit longer to get open than the sodium channels do. But the key thing that this is going to let us do is now on the repolarization phase, instead of this basically just being reliant on not having sodium coming in and potassium going out its potassium leak channels, now potassium can still get out potassium leak channels if we open these guys during the falling phase. But we can also have potassium ions going out these extra channels. So we get even more potassium permeability than usual. And as a result, we get a really quick repolarization phase. And in fact, because potassium's permeability gets so extreme due to the opening of all these extra potassium channels, we can move the membrane not just down to its resting memory potential, but we can almost get down to potassium's equilibrium potential due to how many of these potassium channels are open. So the undershoot is caused by the fact that potassium has higher permeability than usual. So the next slide tries to put all that together in like one big picture. And I really like this one, and we come back to this on the homework. It's just a really good figure. So the idea here is initially we're at resting memory potential. And what would need to happen is there would need to be some kind of an external stimulus that would deliver positively charged ions into the vicinity of the axon that would get us up to threshold. So usually this would be some kind of a generator potential that's coming from some spot out on a dendrite or maybe even just on the cell body of the neuron. And it must be sufficient to begin opening a few of the voltage-gated sodium channels. Once you get a few of them open, you'll get even more positive charges coming in, and that's going to cause all the rest of them to open more or less in mass. And you get this massive opening of sodium channels. So that's what's happening during the rising phase here. And on the figure, you can see that happening. So each of these little recordings, these would be patch clamp recordings of individual sodium channels. It's just showing 3 of them. So this one opens very quickly. This one takes a little bit longer to open. They're not all opening at exactly the same time, but it's within a pretty narrow period of time. You get a pretty substantial opening of all of these various sodium channels. So collectively, if this is the current driven or that's caused by the sodium ions, so we're literally measuring ions moving across the membrane here. If this is the individual components of each channel, this down here would be the sum of all of them. And so we have this massive influx of sodium ions during the rising phase of our action potential. That massive influx of sodium will cause the membrane to get more positive, so we have a huge depolarization that occurs. Then what will happen is the inactivation gates will start to close shut all of these sodium channels. So at this point, all the sodium channels become inactivated. So they're sealed. They cannot allow ions to go through them anymore. And so as a result, you see this dotted line here. This dotted line is kind of our peak of our memory potential. Once we hit that peak, pretty much all the sodium channels have become inactivated, and so we no longer have an inward sodium current. And just about the same time, you see down here, these are patch clamp recordings of individual potassium channels. Just about the same time that the sodium channels have pretty much all closed, you see voltage-gated potassium channels starting to open. And these guys don't have those inactivation gates. They can open and stay open for extended periods. They can open and then close and then reopen. They will stay open basically though until such time that your membrane potential gets back down to resting, and maybe even they'll sometimes stay open even longer than that. So here you've got one individual potassium channel, here's another one, and this would be the collective current of all the potassium ions that are flowing out through those channels. This would be sort of the summed effect of all of them. And so what this is basically showing you is that until your potassium current gets back down to sort of the baseline current that would occur at your resting memory potential, until that occurs, you're going to have this sort of extra downward deflected membrane here. This is the undershoot of our membrane potential, and it's caused by the fact that you have extra potassium permeability and therefore extra potassium current driving as potassium ions drive out of the neuron and cause the neuron to become more negative. Okay, so let me catch up with the narration here in terms of the wording. So the rising phase was caused by more voltage-gated sodium channels opening after the initial ones do. There's overlap, but not all will open at the exact same time, but this collectively is going to cause a large ionic driving force as sodium ions rush into the cell, and that's what's shown by this summed sodium current over here. That causes us to get into this overshoot. So our membrane potential is reaching, or almost reaching, not quite, but it's approaching sodium's equilibrium potential. But then what will happen is the sodium channels will all inactivate, so we no longer have good sodium permeability anymore. There's no more sodium current. And at the same time, voltage-gated potassium channels will start to open, which is shown down here. And that collectively causes a large potassium current to leave the cell. That'll cause you to fall, and then in fact not just fall, but even undershoot the resting membrane potential, because we've got such an excessive amount of permeability of potassium at this point. Eventually, all of these extra voltage-gated potassium channels, though, will close. And once they close, there's no longer extra potassium current, and our membrane potential gets back up to its resting membrane potential of about -65. Any questions on that? That's in great detail, but you know, that's an action potential. I really like the fact you can see the role of individual channels here. I think that's a nice aspect of this figure. One other point, and then I've got a video, and that is these refractory periods. So I said the refractory periods are basically preventing us from firing action potentials too frequently. On the refractory periods, I'm going to draw little red boxes here. Where'd they go? There they are. So there's two refractory periods. There's one that's called the absolute refractory period. The absolute refractory period, as it said a few slides ago, is caused by the fact that all of your sodium channels have inactivation gates. And once those inactivation gates plug up the channels, those channels cannot open again until they reset. And they won't reset until you get back down to your resting membrane potential. So the absolute refractory period occurs from the moment all the various channels close, which is happening right after they inactivate, until such time that they can reset, which won't happen until you repolarize back down to resting membrane potential. So this period then, do I have it? This period basically from the peak up here of your action potential to the point that you get back down and you finish your repolarization and you start your undershoot, that period would be called the absolute refractory period, because all of your sodium channels are inactivated. They cannot open again. And there's just nothing you could do. Like there's no stimulus that could cause those sodium channels to open again until they get an opportunity to reset and eject that inactivation gate. The other kind of refractory period, though, is called the relative refractory period, and that's what's shown here in blue. The relative refractory period is basically just this period of time when it's more difficult to fire an action potential than usual. So unlike the absolute refractory period, you cannot fire one no matter what. A relative refractory period occurs when it's just harder to fire one than usual. And the reason for that is that normally to get an action potential to fire, you've got to go from resting memory potential up to a threshold value to get that process started, to start opening your first voltage-gated sodium channels. And usually you don't have to go very far, 10 millivolts or so. But if you're in the middle of the undershoot, you're down at like minus 70, minus 75 millivolts instead of your usual minus 65 millivolts. To get up the threshold, you need to not only go from here to here, you need to go from way down, in this undershoot, all the way up to resting memory potential, and then from there up to threshold. So because of that, while it's still possible that a really strong stimulus could cause this cell to fire another action potential during the relative refractory period, the fact that you're in the undershoot just means you have a very long distance to go to get up to threshold. And again, threshold will be that point where you start to have your first voltage-gated sodium channels opening. And you just have a really long way to get to go before you can get to that point. The relative refractory period will end when the last of the voltage-gated potassium channels, these extra potassium channels, when they finally close and your membrane gets back down to your resting memory potential. And until that time, you're basically in a relative refractory period. This whole thing happens in like 2 to 3 milliseconds. So it's not like we're dealing with a really long period of time. But once you start your action potential, the first millisecond or so, you're stuck in the middle of your absolute refractory period. And then the last 2 milliseconds or so, you're in a relative refractory period, where it's just harder to fire another action potential. But that's what sets this sort of finite limit on how frequently you could fire action potentials. You've got to kind of wait for these refractory periods to pass before you usually are going to be able to do it. Let me show you a movie. I think we got time.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, 2 key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These 2 events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only, and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
Right. Really like that summary bit at the end. I think it does a nice job. So on the homework for Monday, what I'm going to ask you to do is connect that story. I mean, first, just sort of flesh that story out again. But I'm going to ask you to connect that story to what we did with the Goldman equation. Because with the Goldman equation, we've got our concentration gradients. Those are pretty much fixed. But we should be able to create or recreate something that looks a lot like this just by changing permeability values for sodium and potassium. And so that's going to be one of the challenges on the questions for Monday. So we'll resume there. We'll finish off the slides, and then we will launch into those questions on Monday.